with Unit 3, lecture number 2. Here we will discuss about syntax directed translation evaluation order. So we have already discussed about syntax directed translation in the previous class. So here we will discuss about basically on the evaluation order. So evaluation order for SDT. So first obviously it depends on the dependency, that is the dependency graph. So dependency graph are useful to determine an evaluation order for the attribute instance in a given parse tree. A noted parse tree shows the value of attribute. A dependency graph helps us to determine how those values can be computed. A dependency graph shows the flow of information among the attribute instances in a particular parse tree. An edge from one attribute instance to another means that the value of the first is needed to compute the second. Edges express constraints implied by the semantic rules in more detail. For each parse tree node, say a node labeled by the grammar symbol x, the dependency graph has a node for each attribute associated with x. Suppose that a semantic rule associated with the production P defines the value of synthesized attribute A dot B in terms of the value of x dot C. The rule may define A dot B in terms of other attribute in addition to x dot C. Now, the dependency graph has an edge from x dot C to A dot B, that is at every node capital N, that is the node itself labeled A, where production P is applied. Create an edge to attribute B at N from the attribute C at the child of N corresponding to this instance of the symbols X in the body of the production. Suppose that a semantic rule associated with production P defines the rule of inherited attribute B dot C in terms of the value of X dot A. The dependency graph has an edge from X dot A to B dot C. For each node N labeled B that corresponds to an occurrence of this B in the body of the production P, create an edge to attribute C at N from the attribute A to the node M that corresponds to this occurrence of X. Here M could be either parent or it can be a sibling of N. Consider the production and rule here, semantic rules. So every node N labeled E with children corresponding to the body of this production, the synthesized attribute val at N is computed using the values of val at the two children labeled E and T. You can see in the diagram E1 plus T and value equal to values. So E dot val is synthesized form of E1 dot val and T dot val. An example of complete dependency graph, you can see here is the complete dependency graph. Here 1 to n corresponds to the attribute of the annotated parse tree. So 3 into 5 is 15. So here you can see digit.lex val you get 3, digit.lex val you can get 3, and these values are passed above. Here 5 is passed, is the 3 is passed, 3 into 5 is 15, and this 15 is stored here. Node 1 and 2 represent the attribute lex value associated with two leaves labeled digit. Node 3 and 4 represent the attribute val associated with two nodes of labeled def. The edge of two node 3 and from 1 and to node 4 from 2 result from semantic ruler that defines f dot val in terms of digit dot val. So this is the dependency graph for noted parse tree given in adjacent. 5 and 6 represents the inherited attribute t dash dot inh. The h5 from 3 is due to rule T dash dot inh equal to f dot val. That is the inherited part. So these steps are written very clearly. So here we have edge 6 from 5. So how it works, it's very clear to everyone. You can see from the diagram the node 9 represents the attribute t dot val. The node of node to 9 from 8 is due to the semantic root t dot val equal to t dash dot sync associated with production 1. Now ordering the evaluation attribute. So it can be ordered in different way. So let us consider this is the dependency graph for the annotated parse tree for the given adjacent part. So one of the option can be there. First we can have 1, then 2, then 3, 4, 5, 6, 7, 8 and 9. So this will be okay. Another thing is that you can have all this time also. A 1, then 3, 5, 2, 4, etc. In the S attributed definition, SDD, it is very hard to tell whether there exists any parse tree whose dependency graph has cycle or not. So translation can be implemented using the class of the scene SDD that guarantee an evaluation order since they do not permit dependency graph with cycle. And SDD is attributed if every attribute is synthesized. So if we take this example, you can see L dot val, E dot val, T dot val, and L, F dot val is synthesized. When STD is attributed, you can evaluate these attributes from bottom up orders in order of the parse tree. It is often especially simple to evaluate the attribute by performing the post order traversal of parse tree and evaluating the attributes at the node n when the traversal n for the last time. So the diagram is the algorithm is very clear for bottom of the post order n. For each child c, the node n from left post order c, evaluate the attribute and so on. So these are the post order correspondence. Now L attributed definition. This is the second class of SDT called as L attributed definition. The idea behind this class is that between attributes associated with a production mode, dependency graph can go from left to right and not right to left. Hence L attributed. Each attribute must be either synthesized, inherited, or for rules limited as follows. Suppose there is a production A arrow x1 x2 dot xn and there is inherited attribute x dot a computed by associated by its production rule. We may use 1 inherited attribute associated with the head, either inherited or synthesized attribute associated with occurrence of the symbol x1 x2 xi, inherited or synthesized attribute associated with the occurrence of xi itself. So you can see this diagram also, production rules. The So we'll take one more example. If any SDD, take the following L attributed A arrow B C, the semantic rule can be given as like this. First rule is AS equal to B dot B. Second rule is defined BI equal to F of CC AS. The semantic rule with the control side effect. In practice, translation involves side effect. A disk calculator might print a result. The code generator might enter the type of identifier into the symbol. The SDT we strike a balance between attribute grammar and translation scheme. So we can control side effect in SDD in one of the following ways. Number one, permit incidental side effect that do constraint attribute evaluation. Constrain the allowable evaluation order so that the same translation is produced by allowable order. Example of incidental effect. We can modify some semantic rule to print the result. So this production is okay. It's very simple. Example of the side effect. So in syntax directory definition, figure 5.8 you can see here is the simply declaration D consisting of the basic type T. T can be enter float for each identifier. The For each identifier on the list, the type entered into the symbol table entry for the identifier. Thus, SDT does not check whether an identifier declared more than once or not. So, production 2 and 3 evaluate and synthesize attribute is here. Production 4 and 5 have the rules of function add type. So, id.entry l.inh. So, the number is given here. So, this is the dependency graph for declaration of float id and id. ये चीज़ें डिक्लेयर इसके अंदर की गई हैं. So given a noted parse tree for the following expression. So this is for the your homework. Thank you so much.